The Wittig reaction is really a very interesting reaction. First of all, just for its name, it's named after a German scientist, and so rather than having the W sound, it has more of a V sound, sort of like Wagner. And so this is a Wittig reaction. The specific one that we will be doing in this experiment is actually a Horner-Wadsworth-Emmons modification of the Wittig. Now, where does that come from and what does that mean? It's often referred to as an HWE reaction. That comes from the fact that we're using a phosphonate ester here, so a phosphorus double bonded oxygen and then with two alkoxy groups attached. That's a phosphonate ester, as opposed to kind of the traditional phosphine that would have three R groups, so just simple carbon groups, either aromatic or alkyl groups attached to the phosphorus. And there's some real advantages of the HWE reaction. One is that it tends to allow for the use of mild base. So rather than having to use N-butyl or LDA or sodium hydride for the deprotonation step, here we're able to get away with something as simple as potassium carbonate. Not a very strong base, very mild, can weigh it out at room temperature, it's a simple solid. So let's talk about the mechanism for this reaction then, because it is very interesting. And the whole process is really, really synthetically useful. We're taking a simple aldehyde and we're essentially making an alkene from that aldehyde. We're taking two pieces and coupling them at the aldehyde to form an alkene. And these two pieces could be as elaborate as we want them to be, which means that we can really build up a lot of molecular complexity really quickly, just kind of via a very simple and mild reaction. So how does this work? Well, first step is that these hydrogens here adjacent to the phosphonate ester are actually quite acidic. They're stabilized by the electron withdrawing and resonance effects of the phosphonate ester, but then also the electron withdrawing and resonance involving the ester on the left here. And so these hydrogens are quite relatively speaking, are fairly acidic, and so my base here, which I'm just going to abbreviate as B, just comes and deprotonates and gives me a resonance delocalized charge on that carbon. And so then that kind of primes the reaction to begin. So here I've now got my negative charge there, got the rest of my phosphonate ester. And here, what happens next is that this is essentially just a nucleophilic carbon. I can do a type of carbonyl addition reaction, as I would with maybe a Grignard reagent, or any kind of other kind of nucleophilic addition to carbonyl compounds. So this negative charge comes and attacks my carbonyl carbon of the aldehyde. At this point, I'm going to draw it kind of over here. Sorry for the arrows all over the place. We've got our aldehyde, or what used to be our aldehyde. We've got the tetrahedral intermediate. So I've got my oxygen, the negative charge pointing up, and then I'm just going to draw my hydrogen right there. And then I've got my carbon. Up here is my phosphorus, which is double bonded to oxygen. My other ester groups off of the phosphorus, and then the ester on this side. Now, that gets me initially to this kind of tetrahedral intermediate. But the thing about Wittig reactions and the way the reactions progresses here is that we form a four-membered ring. Because oxygen has a very large affinity for phosphorus, we actually get this negative charge on oxygen swings over and just attacks that phosphorus. We can think about swinging that bond up to sort of give a similar tetrahedral intermediate. I'm going to draw that product. Actually, I'm going to just erase this and sort of redraw the product. So here, four-membered ring. Here, this is my, I guess, oxaphosphocyclobutane, or you could think about it in that way. I've got this four-membered ring. Technically, this bond would be up there. Of course, I could think about this coming down and kicking off one of these groups here, so I could redraw my double bonded oxygen and get rid of one of these groups here on phosphorus. But I have essentially a four-membered ring at this point. I'm going to erase the hydrogen just for clarity, or maybe redraw it down here. And then the key step in forming the alkene here is essentially just that this oxygen, the carbon-oxygen bond, breaks and goes to form a double bond between oxygen and phosphorus. The carbon-phosphorus bond breaks and goes to form the alkene. So this gets us then to our product. Plus we have some byproduct that involves the phosphorus and oxygens there. So we're going to have some phosphonate ester byproduct. Now, what have I drawn going on here with the product? I've drawn the alkene, but then I've drawn these really wiggly lines for the hydrogen that's on this carbon. So there's a hydrogen I sort of omitted. And then the ester. Well, what I've drawn there, and what the key point of this experiment is looking at, is what is the regiochemistry of this double bond? Is it a Z alkene? Is it an E alkene? Often we think about this as being, is it cis or trans? And how do we tell what kind of selectivity or any selectivity does this reaction give? Well, what we're going to be able to see is we're going to be able to determine this using proton NMR. So it turns out that HWE reactions are generally very stereoselective. It's going to produce one stereoisomer here, either the E or the Z alkene, or cis and trans if you want to use kind of the simpler nomenclature here. You just have to be a little careful because cis and trans doesn't always apply, whereas E and Z is kind of universal. So how do I tell the difference by proton NMR? Well, the way that I tell is by looking at the alkene proton. So there's going to be two signals, a signal for this hydrogen and a signal for this hydrogen. Now this hydrogen might be opposite it, or it might be on the same side as that hydrogen there. And each signal is going to be a doublet. They split each other. And so they should have the same coupling constant, the same degree of splitting. It'll be a signal that integrates to one proton. There should be two of them since they're in different environments. But then what really tells me whether this alkene is Z or E has to do with the coupling constant, with how much splitting there is between the two peaks in the doublet. So how strongly do these hydrogens split each other? I can go in and measure the difference between those two peaks in hertz here in frequency, and then that difference is known as the J value, or the coupling constant. Now, it turns out that cis alkenes versus trans alkenes have very different coupling constants. So cis alkene, where the two hydrogens are on the same side, these normally have J values on the order of about 5 to 12 hertz. So that would be my coupling constant for a cis alkene, whereas for trans, these are normally much larger. So this would be somewhere on the order of about 12 to 18 hertz for my coupling constant. Typical values for a cis might be around 8 hertz. For a trans, maybe around 15 or 16 hertz here, but it really could be anywhere in that region depending on kind of the other reaction specifics. But it just has to do essentially with how strongly these two hydrogens couple to each other and how strongly they split each other. And in the trans geometry, as I've sort of drawn with here, although we don't know that the hydrogen is on this side, we have stronger coupling between the two in the trans than we do with the two in the cis geometry, and so we have larger coupling constants. So what we'll be able to do is we will measure the NMR for this product, and then we will look very specifically at the alkene signals, the CH signals here, and we'll look at the coupling constant, the splitting between those two peaks, and measure that in hertz so we can determine whether this produces predominantly a cis or trans or E or Z geometry for that alkene product. In terms of reaction specifics, it's a very simple reaction. I'm going to just literally just mix these two together with water actually as the solvent. This is another thing. The HWE modification is often very tolerant of solvents that maybe a normal Wittig reaction might not be. And I'll simply throw in my base and heat the reaction to reflux. We'll talk about a reflux in lab. And then essentially just let that reflux strongly for about 15 minutes, cool the reaction, and we'll just filter to collect the solid product and then perform a recrystallization to purify that material. So with that introduction, let's grab our stuff, head up to lab, and get this going. Here we are in lab, all prepared to set up the Wittig reaction. We have our liquid reagents, our triethyl phosphonoacetate, our 4-methoxybenzaldehyde, otherwise known as p-anisaldehyde, our solvent, which is just distilled water. Then we have our solid reagent, which is potassium carbonate. Now the reaction itself is conducted in a round bottom flask with a reflux condenser attached. Now, we're familiar with a condenser from the distillation lab, and it's actually pretty much identical here. It has the water jacket and the central bore. But in this case, instead of condensing the vapors and having them drip into another flask, the reflux condenser is simply placed on top of the reaction vial, and then the solvent vapors condense directly here and drip back down into the same reaction vial. This is a very convenient way to add a lot of thermal energy into the system without losing volume due to solvent evaporation. So here you have kind of boiling of the solvent and the recondensing, that liquid drips back down into the reaction flask. So what I'll do with the system here is I'll first weigh out my solid reagent, my potassium carbonate, and add that into the reaction flask with a Teflon-coated stir bar. Now, technically, the procedure that you were given says to do this after you've added the liquid reagents, but it's generally a good practice to add your solid reagents and your stir bar first at the very beginning. This minimizes any kind of splashing when you add those solid reagents or the stir bar later. So we'll go to the balance and weigh out our potassium carbonate, add it into the round bottom flask. We'll then take the reflux condenser. We want to make sure that we have a really good seal between the round bottom flask and the reflux condenser. To help with this, what we'll do is we'll take a little bit of vacuum grease. We'll just put just a little bit on the end. I'll make a little line here of vacuum grease there on that end of the ground glass joint. I can then connect this to the round bottom flask and just sort of spin it around, make sure that it's kind of uniformly coated with vacuum grease. This will ensure a nice seal between those two without any kind of leakage that might lead to solvent loss. And then the other thing I'll do is I want to really make sure that these two pieces stay together. So after I've added my solid reagent, I'll come back over here, I'll add my liquid reagents, and then I'm going to connect the round bottom flask to the reflux condenser a little bit more thoroughly. The way to do this is I've got a little O-ring here, a little rubber O-ring that's going to fit onto the end of the reflux condenser. Sort of sit that there. Actually, before I do that, I need to put this little cap here on the reflux condenser, like so. I'll put then the little rubber O-ring on the end there. And then I can now put this together and then screw this down. In addition to the vacuum grease that I put, this now makes a really firm seal. It will hold those two pieces together. I don't need to clamp on the round bottom, which would be rather difficult, but I can simply clamp up here on the condenser and then bury that round bottom, or the bottom half of that round bottom, into a sand bath and heat the system above the boiling point. Heat it a good amount, or set the hot plate a good amount above the boiling point so that we get a good strong boil and reflux as the vapors condense back here in the condenser and drip back down into the reaction flask. Now the vapors probably won't condense very well if I don't have water flowing through the condenser. And so here I've got some tubing. I'll run the inlet to the bottom of the reflux condenser. I'll run an outlet to the top that runs back to the sink. The inlet will come from the faucet. The outlet will go back to the sink. And that way I'll kind of establish a slow, but not too slow, flow of water that will provide the cooling in the condenser. So with that bit of an introduction, let's head over to the balance and weigh out my potassium carbonate. We'll add that into the reaction flask, then come back and add my liquid reagents, and then connect the reflux condenser, bury it in the sand bath, and begin the heating. This is a little bit more than I have technically set, but since it's simply acting as a base in the reaction, it's sufficient. I'll add this into my reaction flask now. Now that we've weighed out our solid reagent, we can now dispense our liquid reagents. So we need 0.5 milliliters of distilled water. That would be 500 microliters. So we'll set this to be 500 microliters using the micropipette. We need 1.4 milliliters of the triethyl phosphonium acetate. We can do that with 2 deliveries using the micropipette. We'll do essentially 2 700 microliter deliveries. Lastly, we need 365 microliters of the p-anisaldehyde. So we'll set that here. Now that we have dispensed all of the liquid reagents, we can attach the reflux condenser. Carefully tighten that down. We'll now clamp this into the sand bath and then attach the water hoses. We now have a reasonable stream of water. We can begin heating the reaction. We set the hot plate at around 250, and we're going to set the stirring very high here to make sure we have very good kind of mixing, especially with those with the solid insoluble reagent of the potassium carbonate. set this up close to 1100 for the stirring, and then we can begin the reaction. At this point, we've let the reaction run for about 10 to 15 minutes. We'll remove it from the heat. So we'll turn the hot plate off, but then we'll remove it from the heat by simply lifting this up out of the sand bath. Let that cool. And then once this is cooled down to room temperature, and we've got some solid material that will crash out, we'll take this over and filter and collect that solid material by vacuum filtration. The material has now cooled and solidified, so you can see a lot of solid here in the reaction flask. I'm going to add a little bit of water and scrape this onto the filter, and then rinse that with a couple portions of just distilled water. So I'll turn the water aspirator on. We'll wet our filter paper. Make sure that adheres really nicely. I'll go ahead and scrape this. Sort of swirl that up a little bit. Looks like we're going to need to add some water in order to really have any volume to work with. So sort of. And it helps to kind of homogenize things as much as possible. The potassium carbonate could be one solid that's present here, but that should be soluble in water, whereas our product should be insoluble in water. And so by mixing everything up, we can hopefully sort of separate out those two and get the potassium carbonate mostly solubilized. So we'll pour that onto our funnel. We'll rinse this again with some water. There's some more solid material remaining. You might notice that it's filtering very slowly. This is because we actually have some kind of crystalline material here, and that relatively small crystal size is kind of clogging up the filter, or causing it to filter very slowly. So we'll pull air through these crystals for a while to try to dry them. Unfortunately, we cannot place the product in the oven to help dry it further because the melting point of the product, of the Wittig product, is less than 100 degrees Celsius,
and the oven is normally set above that. So we'll pull air through this for a while to get our crude product, which we can collect, and then we will recrystallize to purify our sample further. There we are, all set to get our crude, mass, melting point, and NMR. We'll set a small amount aside for melting point and NMR measurements, and then we'll retake the mass before recrystallization. To recrystallize the crude material, I will use a 2-solvent recrystallization rather than the usual single solvent recrystallization that we have done so far. So here on the hot plate I have some 95% ethanol that is warming up. What I will do is I will take and add that 95% ethanol slowly to the beaker containing my crude product until the solution just barely dissolves. After everything is dissolved, I will then take water and add it dropwise to that solution until I start to see the signs of a precipitate formation, so signs that the solution is getting cloudy. After that solution just begins to get cloudy, I'm going to add more 95% ethanol to it just to the point where everything is perfectly soluble. At that point, I'll be essentially a saturated solution at the high temperature. So I'll add absolute ethanol, or the 95% ethanol, just until the solution gets clear again. And then I'll remove the beaker from the hot plate and let it cool. And then based on the differences in temperature, or the solubility at the different temperatures, I should then get a good recrystallization. So we'll let the ethanol warm up, and then once it's warm, we'll begin this process. My ethanol is good and boiling hot, so I'm all set to begin the recrystallization. I'll take my material here, not set it on the hot plate because I don't want to melt my material. I'm just going to start adding the hot ethanol carefully to this. Start to swirl it. At this point I can set it on the hot plate. Maybe once I dissolve a few more of those chunks of material, add just a little bit more of that boiling hot ethanol. There we go. And start to set that on the hot plate here. Swirl it. We go in and try to break up some of these larger chunks. Swirl that solution up, suck some up and squirt it around. We've almost got everything dissolved. We still don't quite have everything dissolved. still some insoluble material, so I'll add a little bit more of this boiling hot ethanol. You can see the ethanol in the beaker starting to boil here. Getting good and hot. At this point, it appears that everything has dissolved. So at this point, I want to start to add water dropwise, very slowly. Start to add this while it's still hot. I'm going to add water very slowly. I do that a little bit more than dropwise, just until the solution starts to get cloudy. Sort of see it as I'm adding. There's a little cloudiness at first, and then it disappears. Swirling that. Still clear. You can see that kind of cloudiness starting to appear. Ooh, there, you see some, and it sort of goes away. See a little bit of that cloudiness. Zoom in here. Still putting a lot of heat into the system, which is good. We want this to stay good and hot. Start to add some more. You can see that cloudiness there as I've sort of added water. Sometimes a little precipitate will form when I do that. And when I swirl, that cloudiness appears to go away. Oh, well, in this case, if we look very closely, we actually now do have some material that's come back out of solution. And now I'm at the point where I've added enough water. I need to just add enough ethanol to get this back to dissolved, to fully dissolved. So we can even just let this sit on the hot plate for a little while. See if we can increase the temperature. It cooled down a little bit as I added that. As I added the water. So put this on here. Keep that kind of good and hot. Continue to swirl that. So we're very, very close to that just soluble phase. We need to add just a little bit more ethanol. Kind of add it along the side of the walls here. Brush some stuff down. And there, as we did that, it appears we've reached that point where we are just soluble again. The solution is redissolved any material that came out there for just a moment. So let that sit there just for a moment. Make sure it's good and hot. And then we'll go ahead and take this off the hot plate, let it cool, and look for crystals to form.